At Sunrise, this is empty West Texas. Oil is trapped in rock no one can see. A rig and production system must turn that invisible promise into measured liquid without losing pressure control. Soon a rig rises, turns steel, and builds a path underground. Then it leaves. What may remain is Texas's familiar pumpjack nodding over a smaller site. But a pumpjack does not drill, and it may not be needed when first oil flows. So what does each machine do? Follow one well from target to tank. The rig makes the hole. Mud carries rock and pressure evidence back. Steel and cement make the route durable. Completion connects pores to the well. Surface equipment controls and separates the mixture. Only later might a pumpjack add lift. The question is how each uncontrolled step makes trapped oil move. The end game is not a wild gush. It is a controlled route from pore to pipe. First, remove the easiest wrong picture. The crew is not aiming for a black underground lake. A reservoir is rock that can store and transmit fluid. Zoom between the grains. The gaps are pore space. Some pores are isolated. Others connect, forming narrow paths through the rock. Oil occupies part of that connected space beside water and gas. Porosity describes how much void space exists. Permeability describes how easily fluid can move through the connections. A rock can store oil and still resist flow if those passages are tiny. That is why the target is not just a depth. It is an interval with the right rock, fluid, pressure, thickness, and economic promise. In this representative Permian well, the productive layer is notably tight. A vertical hole would touch only its thickness. A horizontal section can remain inside it for far longer. Before the well can turn, the crew must make a stable vertical path. The problem is physical. How do you transmit force and rotation through steel without losing control in the field? The drilling rig arrives as a temporary factory. Its tower provides height for handling pipe. At the rig floor, a rotary system turns the drill string while weight presses the bit against the bottom. Rotation travels down the steel. Roller cone teeth roll and crush rock. Fixed PDC cutters shear it. Watch the contact. The bit does not spin in open space. A cutter loads rock, stress concentrates, a fragment breaks free, fluid clears the face, and the tool advances. That repeating cycle is drilling. The string must lengthen too. Drilling pauses, another pipe section is connected, pumps and rotation start again, and the well deepens. The derrick handles pipe, but cutting happens far below. None of this proves producible oil. The crew sees torque, weight, penetration rate, vibration, and fluid behavior. Rock must still send evidence back. That requires a second machine running through the first, a closed liquid loop. Why pump liquid down when the desired liquid must eventually come up? Because drilling mud has jobs before production. Pumps drive it down the hollow drill string. It exits through nozzles at the bit, sweeps across the cutters, and turns upward outside the pipe. That outer path is the annulus. Returning mud carries broken rock upward. Follow one fragment. It formed at the bit, joined the rising stream, and reached a shale shaker. The screen lets liquid fall through for treatment and reuse while larger solids travel away. A fresh cutting can reveal color, texture, minerals, and signs of hydrocarbons. An oil-stained fragment is exciting, but it is not first oil. The sample has traveled and mixed. Its origin must be matched with depth, time, drilling behavior, gas readings, and downhole measurements. The return proves contact with rock. It does not prove oil can flow at a useful rate. Mud is doing something even more important. The weight of this moving column helps hold the well under safe control. Rock around the borehole contains fluids under pressure. If the well offered an easier path and nothing pushed back, those fluids could enter. Drilling mud supplies counter pressure. Near the top, little fluid rests above a point. Near the bottom, the column contributes much more weight. Greater true vertical depth increases pressure. Greater mud density increases it again. That sounds like a reason to make mud as heavy as possible, but an upper limit matters. Push too hard and rock can fracture. Mud may escape into the formation, removing the support the crew meant to increase. Safe drilling therefore lives inside a pressure window, above the pressure that emits formation fluid, below the pressure that breaks the rock. Real wells also include circulation friction, temperature, changing geometry, fluid behavior, and transients. So this column is a foundation, not a complete model. Pumps, return flow, pit volume, gas, and pressure are watched together. The goal is a known margin while the bit moves. Once this section is stable, how can a steel path that began straight down turn sideways through solid rock? A drill string is flexible across a long distance, though each section feels rigid. Near the bit, a directional assembly can bias the cutting action. Measurements while drilling report inclination, azimuth, and tool orientation. Logging tools can estimate properties of the surrounding formation. Selected data may return as pressure pulses through the controlling mud column. This is not a live camera. It is a narrow stream of measurements. The crew builds angle gradually. The tool face is oriented. The bit removes slightly more rock along the intended side. The bore curves instead of forming a sharp elbow. Measure, steer, drill, and measure again carefully. Keep the gold point on the near bit tool as the path bends toward the target. Once the planned inclination is reached, the curve settles into a horizontal section. Each new meter can stay beside oil-filled pore space. Direction alone is not enough. Formation readings and cuttings must agree that the tool remains in the intended rock. A safe curved hole in the wrong layer would still fail. When trajectory and geology converge, the crew has reached the target, yet the raw hole is temporary. It must become a permanent isolated pressure path. The well is built in stages because one open hole cannot safely expose every formation at once. Steel casing is lowered into the section already drilled. Cement is pumped into the space outside it and placed around the chosen interval. The materials have different jobs. Casing provides a safe pressure-rated conduit. Cement supports it and seals the surrounding annular space, helping keep formations apart. Once checked, drilling continues through a smaller opening. More casing strings follow each time. The well becomes nested shells, widest near the surface and narrowest near the target. Each stage isolates water-bearing rock, weak intervals, different pressure regimes, or the final production section. Later work must pass through the diameter left earlier. At the target, casing isolates the long horizontal section. The crew has built a durable route to the reservoir, but the route is still deliberately sealed from it. Drilling was about reaching and constructing. Production requires the next phase, completion. Now the tall drilling rig leaves. Its job is finished. A new completion spread takes over because reaching and producing are different events. Steel and cement separate the well from oil-bearing rock. Openings must be made. Perforations form short tunnels through casing and cement into the reservoir. In permeable rock, that may be enough. Our representative well is in a low permeability interval, so the completion adds another step. Fluid is pumped at high pressure into selected stages. Fractures open away from the well bore according to rock stresses. Proppant grains travel with the fluid and help hold conductive paths open after pumping. Hydraulic fracturing is a specific choice here, not a universal feature of every oil well. It does not create oil, it connects more of the oil-filled pore system to the horizontal well. Stage by stage, isolated sections become one controlled production path. When fluids return, flowback and testing begin under measured pressure and control. The first material at surface is not necessarily clean crude. It is a changing mixture that must be controlled, measured, and separated. This is the payoff the old picture never showed. Reservoir fluid enters through perforations, moves into the well, and rises through production tubing. The stream can contain treatment water, formation water, gas, solids, and oil. Nothing sprays into the air. Valves directed into surface equipment. Inside a separator, velocity drops, and gravity helps the phases divide. Gas rises, water settles. Oil forms its own layer and leaves through a controlled outlet. Follow the gold-black stream. It crosses the vessel, passes a meter, and enters a tank or gathering line at a known rate. First oil becomes unambiguous here, not as a gush at the bit, but as a measured product separated from the mixture. Samples test composition. Instruments measure rate. Pressure stays controlled. Water and gas follow their own routes. The end game is visible. The geological target has become a controlled surface flow, and the giant drilling rig is already gone. Compare the site before and after. The derrick, mud tanks, pumps, and pipe racks once filled the pad. During production, a compact wellhead remains with a separator, tanks or gathering lines, meters, and valves. The wellhead controls the stream. The separator performs the first sorting job. Storage or pipelines carry saleable oil onward. This smaller arrangement may operate for years, but conditions change. Early on, reservoir pressure may move fluid through pores and up tubing. Later, pressure and rate can decline. Water fraction can change. Gas can leave solution. Deposits, wear, or restrictions can alter flow. Operators compare pressure, rate, fluids, and equipment before intervening. Artificial lift means adding energy to the fluid column. Options include gas lift and electric submersible pumps. The familiar Texas beam pump is another. If this well receives one, it arrives after drilling, completion, and first production. Its nod is the surface end of a mechanism reaching down the tubing. Watch the pump jack as a linkage, not a symbol. A motor turns a crank. The crank pulls a connecting rod. That rod rocks the walking beam around its pivot. The horsehead guides the polished rod almost straight up and down. Below ground, that rod connects to a sucker rod string and a downhole pump. The surface motion is rotary first, then rocking, then vertical. At the pump, a plunger and 2 check valves turn that motion into upward fluid movement. During one part of the stroke, pressure differences admit fluid into the chamber. During the other, one valve closes, another opens, and the lifted column advances. Every surface stroke corresponds to a pressure change inside the buried pump chamber. Each cycle adds energy to fluid that no longer reaches surface fast enough on reservoir pressure alone. The pump jack does not suck oil from a cavern. It lifts fluid already entering the completed well from connected pores. Speed and stroke must match what the well supplies. Pump too aggressively and the pump may not stay filled. Match to the system and the slow nod supports steady production without the drilling rig returning. Return to the landscape and trace the answer. Oil begins in connected pore space. Drilling creates a path while mud returns, cuttings and pressure evidence. Tools turn the well to stay beside more reservoir. Casing and cement make the route durable in separate formations. Completion opens connections and holds fractures open with proppant. Reservoir pressure moves the first mixture into production tubing. The wellhead controls it. The separator divides gas, water, and oil. The gold-black stream enters a tank or pipeline where its rate is measured. If natural energy weakens, the pump jack's crank, beam, rod string, plunger, and valves add lift stroke by stroke. So the tower vanishes and the nodding machine may remain. One drills and constructs, the other can help produce. The end game is the controlled chain from pore to well to separator to pipe.